Speed and Distance 101. Today, I will discuss the range of an e-bike, as determined by speed, and the amount of battery amp-hour available. First, let me point out, due to the number of variables, this is not an exact science, but will give you some insight as to how far you may be able to travel, based on the amp-hour capacity of your e-bike's battery. There are three main forces that determine the amount of current required to drive the e-bike's motor to move it at any given speed. First, gravity, the weight of the rider, the e-bike, and any gear and accessories. Second, friction, which is influenced by gravity/weight. The wheels and tires create the bulk of friction through the axle and bearings, and the contact surface of the tires. The third force to deal with is wind resistance. As the e-bike increases speed, the velocity has an exponential effect on the resisting wind force. Without being influenced by other outside forces, such as hills, headwinds and tailwinds, the e-bike's controller will try to send the same amount of current to the motor, even as the voltage level drops. The designated amount of current will be progressively higher as the power assistance levels go from PAS modes 1 through 5. A headwind will increase the wind resistance, resulting in a reduction in speed. The e-bike's controller will send more current to the motor to try and maintain speed. Due to the increased current going to the motor, the battery's voltage level will drop. A tailwind will decrease the wind resistance, resulting in an increase in speed. The e-bike's controller will send less current to the motor due to the increase in speed. As a result of the decreasing current going to the motor, the voltage level will rise. Riding uphill will induce gravity that will hold the e-bike back, resulting in a reduction in speed. The e-bike's controller will send more current to the motor to try to maintain speed. Due to the increased current going to the motor, the battery's voltage level will drop. Riding downhill will induce gravity that will push the e-bike forward, resulting in an increase in speed. The e-bike's controller will send less current to the motor due to the increase in speed. As a result of the decreasing current to the motor, the voltage level will rise. I have developed a formula to estimate the range that an e-bike rider can travel on a fully charged battery. To provide the correct data for this formula, each individual rider will need to determine the amount of current/amps required to maintain a constant speed for each of the PAS modes and full throttle. The current/amps required will vary depending on the weight of rider and gear. Also, this formula is based on a level road surface with no headwinds or tailwinds. Hills, headwinds, and tailwinds, depending on their extent, can greatly affect battery range. Also, to be noted, the amp-hour ratings on different batteries can be misleading. This formula is simple, Algebra 101. If it is used, and the results are not in line with your findings, then it is very likely that the amp-hour rating of your battery is not correct. From field data that I've collected over several hundred miles of riding my e-bike, I have created a battery percentage level chart. This chart should apply to all 48-volt batteries, which have a fully charged voltage of 54.6 volts, and their e-bike controller shuts the motor off at 41.4 volts, plus or minus. This graph shows the percentage of battery charge at corresponding voltage levels. These percentage levels were the results of field data taken from two different data sets. Even though the two data sets were not in 100% agreement with each other, it was within 2% deviation. Here is an example, using this formula. For the purpose of this example, the e-bike will be in PAS mode 3. The battery is rated at 10.4 amp-hour. The observed current is 5.7 amps. A travel speed has been observed at 15.6 miles per hour. The results, using this formula, is a distance of 28.6 miles. Let me try to explain why riders have such a problem in trying to determine the range of an e-bike. I will create a scenario using my distance formula. A rider comes to a mile-long hill, and he is in PAS mode 3, on level road, with no wind. While proceeding up the hill, he notices that his e-bike's speed dropped from 15 miles an hour, down to 10 miles an hour, and that the current to the motor rises from 5 amps to 18 amps. Using the distance formula, 10.4 amp-hours divided by 18 amps, times 10 miles per hour, the distance equals a range of 5.8 miles. On the level road, the rider was traveling at a rate of range at 31.2 miles, but now going up the hill, the rate changed to a distance of 5.8 miles. That is a 537% decrease in the battery's distance rate, so, for that 1 mile of hill, the battery lost 1.8 amp-hours. To determine the distance now, subtract the 1.8 amp hours from the 10.4 amp hour battery, which equals 8.6 amp hours. Using the formula again, assuming that the remaining distance will be on level road, the range is 8.6 amp hours divided by 5 amps times 15 mile per hour, equals 25.8 miles. Add the 1 mile of hill, for a total of 26.8 miles. Conclusion: the 1 mile of hill shortened the battery range by 4.4 miles. You can see by this scenario, how easily the range can be affected by outside forces. This was just one hill. Wait a minute, you might say. What about the other side of the hill? Okay, for every uphill, there's usually a downhill. Let's change the scenario a bit. There are 4 1-mile hills along this route. In going up these 4 hills, we lost 17.6 miles of the original level road, and yes, for each uphill, there's usually a downhill, and that would equate to 4 miles of downhill. Assuming the e-bike is coasting down the back side of these hills, that would be a gain of 4 miles. So, out of the original 31.2 miles, 17.6 miles were lost, and 4 miles were gained, which now give us a total distance of 17.6 miles. You can clearly see that throwing a few hills into the equation, the results will be greatly affected. In the 4-hill scenario, the range of the fully charged battery was half the distance of the level road with no hills. Similar scenarios could be made, dealing with the effect of headwinds and tailwinds. When traveling in one direction, headwinds can be a curse, and tailwinds a blessing. An out and back trip, the headwind and tailwind would possibly be a washout. The human factor, or the power that the rider contributes while in power assist from the motor. E-bikes, such as the Electric XP, have a motor rating of 500 watts with a peak rating from 700 watts to 800 watts. Using a 500 watt motor rating, the e-bike produces 0.67 horsepower, with peak power above 1 horsepower. Depending on the source, cyclists can produce anywhere from 25 watts to 400 watts of sustained power. Broken down into the experience level of cyclists, the casual neighborhood cyclist may produce from 25 to 50 watts per hour, the novice cyclist may produce from 75 to 100 watts per hour, the avid fit cyclist may produce over 100 watts per hour, and the professional cyclist may produce an outstanding 260 to 400 watts per hour. As you can see, that's a heck of a range. Where do e-bike cyclists fall? My guess would be within the first 2 categories, 25 to 100 watts per hour. If any e-bike riders were above the first 2 categories, they would likely not be riding an e-bike. Also, many of us are older cyclists. As some studies show, there is an age-related decline in a cyclist's performance of about 24 watts or 7% per decade. The 7% are for those e-bikers that started out at the low wattage end, and likely use throttle only when riding. A good way to test your human power, while riding your e-bike, is to take it out on a level road. While there is no wind blowing, take it out of any power assist mode. Place the e-bike in a comfortable gear, then pedal. Make a note, at the speed that you feel comfortable pedaling in. Once that is complete, put the e-bike in any PAS mode, and use the throttle only, do not pedal. Make sure that the controller's LCD monitor is set in the current display. Turn the throttle until the speed matches the speed that you were previously pedaling, with no power assist. While holding this speed at that matching level, make note the amount of current, in amps, that are showing on the monitor. This will be equal to the amount of power that you were using to pedal the e-bike with no power assist. In summary, I hope that I have given you some insight to the complexities of determining an e-bike's battery range. I only touched the surface of variables that can affect an e-bike's range/distance. Without these variables/outside forces, and in a perfect world, it is very easy to determine the e-bike's range. I hope that you've gained some knowledge as to why there are so many misconceptions about an e-bike's battery range. So, the next time you see an e-bike's claim of a 60 to 80 mile range, don't think that it is impossible. If you travel slow enough, with the right conditions, most e-bikes could achieve such claims. Speed is the key word to the equation. Thanks for watching.